I'm Kartik Dhingani, 23 UCC 556, and we will be looking at my DL project. Here we will go through many topics like vanishing gradient, exploding gradient, regularization techniques, and architectures such as VGG16 and ResNet 150. So let's take a dive into it. The first code block is basically us downloading the data and unzipping it, splitting it into directories for training, testing, and a smaller data set for exploring through gradient descent problems. Uh, we can see that we have created two subdirectories, each having 100 images in them. And the next code block shows us the model for vanishing gradient. Here we resize the data, rescale it bit so that it has value of 0 and value between 0 and 1. And here we create a model which first flattens it. So what it does essentially is create a 2D image into a 1D. And then we can see that we have a dense layer, 20 of them, each having 50 units. And these dense layers are having sigmoid activation function. And the next, we have another dense layer, which is our output layer with 1 unit and a sigmoid activation for binary classification. So the next model is compiled using SGD optimizer with a low learning rate of 0.01 and binary cross entropy as the loss function. Then, as we can see in our output, there are very nominal changes in the accuracy, and we can see there is not much change in loss. This is a classic sign for vanishing gradient, as the process or output or accuracy seems to get stagnant and be very low overall. The next up is our exploding gradient. Here we import random normal from TensorFlow Keras to initialize weight and matplotlib so that we can use create a function, which I will show you in a second, which is used to basically plot and reused for printing the results that we encounter further in our project. So looking going towards exploding gradient, here we have essentially the same structure, but the key difference is this part. Here, what we do is give or initialize higher or bigger weights with a standard deviation of 1.5. So that what it does, higher weights, as we all know, corresponds to an exploding gradient problem. As we go down, this is the function that I was talking about. This function is used to plot graphs and show our results out when we compile or get result moving further, going further on. So as we can see, we trained it over here, and our accuracy is 0.46 and loss is 9. The NaN loss is the sign that we are having an exploding gradient problem in the code. Moving on, as we can see, this part we discuss our regularization techniques. Sorry, this part we will discuss our overfitting model. So what overfitting is, as we all know, that model performs exceptionally well for the training case, but it fails or does not give as good accuracy as we had for training. So here we created our same RSCNN model using convolution 2D, and the input shape will be 150, 150 height width and 30 depth. So 3 layers. We use max pooling between each convolution layer. So total of 3 max pooling layers, 3 convolution layers, and then we flatten it. So convert it into 1D. Then we get an output. So for the dense layer, we use sigmoid activation at the end as we want to classify it into either a cat or a dog and ReLU overall for the model. Optimizer used is atom, binary cross entropy, and matrix accuracy. We fit the model, we run it for 20 epochs, and we see that our accuracy at the end goes to 100, but validation accuracy is not as good, and validation loss also keeps on increasing rather than decreasing, as we can see it in the graph and down here in a percentage. Moving forward, this is our demonstration for how regularization works. As we all know, regularization helps us counter the overfitting problem, and we use dropout, L2 norm, and data augmentation for help regularize as regularization techniques and reduce the overfitting. As we can see, ideally what should happen is the training and validation graph should be close to each other, not as we saw earlier. And the same thing can be seen in the output. We train this model for also 20 epochs. The CNN architecture stays the same. This is the custom CNN that we are using. Later on, we will discuss about other deep learning architectures also. So here we can see that the training and the validation curve for accuracy are much more closer to each other, and the loss for training and validation is also decreasing as compared to what we saw for overfitting, which was loss increased and the validation accuracy was kind of stagnant. Loss increased and validation accuracy was stagnant. Here we can see that training accuracy and validation accuracy are also near about same, like close to each other, rather than being a big difference as we saw in overfitting. So this is our custom CNN architecture that we used for past two code blocks. This also faces the same issue of overfitting. Hence, every CNN custom model should include a regularization technique in them. So we will discuss VGG16 as we talked about. So this cell demonstrates this cell basically demonstrates learning using pre-trained VGG16 model. We use convolutional base of VGG16 and add custom classification head for our specific tasks. We add a custom classification head on top of frozen VGG base, as we can see, and then we create the final VGG model by defining the input and output layers. We are also using regularization techniques over here, as we just saw that any model without regularization is prone to overfitting. The output shows the training process. As we can see, we run for it for 10 epochs, and our training accuracy goes from 67 to 96, and our validation accuracy goes from 0.8 to 0.88, and loss decreases. So it's a good sign that we are not going towards overfitting problem. So the final accuracy for training and validation comes out to be these. Later, we have a ResNet 152 architecture over here, as we we were supposed to discuss ResNet 150, but the problem is ResNet 152 is standard version available in Keras and is functionally equivalent to the task. We again create a base model. Uh, we use global average pooling to reduce dimensions. A dense layer of 1024 with activation ReLU is created. We use dropout for regularizing, and our output would be a single unit dense layer and a sigmoid function for categorizing our output into a cat or a dog, as we have as the model is classification problem with our data set. The ResNet model is compiled over here. We use learning rate, which is very low, and a low loss function of binary cross entropy. We run this for 10 epoch, and we see that our accuracy goes from 0.53 to 0.61 by the end of 10th epoch, and validation accuracy goes from 0.55 to 0.61. Here also using dropout has helped us to counter overfitting, and we can see that the trend for accuracy between training and validation is similar, and the losses also in a decreasing fashion. So this was my presentation for my DL project. Thank you for your time.